we can start because this is actually, I have a lot to cover in this first lecture. So I'm going to take it up exactly where we left it off yesterday. So yesterday we talked about the Ericsson-Pekes model, which is an empirical model of industry dynamics with a big benefit of it being able to be adjusted to many applied situations of interest, from firm entry and exit to all sorts of different types of investment, even competition in prices or quantities that might be dynamic. And we also saw one example coming from Benkard 2004, which was learning by doing in the aircraft construction industry. And that was an empirical example. However, we didn't really estimate the model. We basically were fortunate enough to, that's great, thank you. We were fortunate enough to have really good data to get some of the dynamic parameters. And then we calibrated several other parameters of interest, like the entry and the exit cost. So today we are basically going to discuss, we're going to take exactly the same model and discuss how to estimate the primitive parameters of interest. So what are the parameters that we need to know? So if we want to conduct policy analysis in a world of dynamic oligopoly, we're going to need to know parameters such as the per period profit function. We're going to need to know transition probabilities. And we're going to need to know the distribution of parameters such as the entry costs, the scrap values, and the investment costs that we saw yesterday. Okay? These are essentially the core dynamic parameters that are hard to get and that we're going to spend most of our time talking about. Okay? So sometimes these can be estimated offline, and by offline I mean without really taking into account the dynamic structure of the model. The example we saw yesterday was an extreme case because we basically managed to get all of the parameters offline one way or another. This is very rare. But in most applications I will talk about today except one, the per period payoff is another example of a parameter that can be estimated offline. And I alluded to this yesterday that in many cases, if you have a per period payoff function that is a sort of Cournot or Bertrand, differentiated Bertrand game, then often we can actually get these parameters with static methods like PLP or just straight up demand and supply in the case of Cournot, and we don't need to worry about the dynamic implications. But when it's going to come to entry costs, scrap values, and investment costs, we will never be able to do something without the dynamic, the structure of the dynamic model. So what is our data that we have to estimate these parameters? Most often, our data is basically going to have firms' actions and the states. So I'm going to know that at this particular state, you chose to enter. At this particular state, you invested $100 million, and so on and so forth. And we're going to use essentially the different actions that firms are taking at different states and try to estimate the underlying dynamic parameters like entry costs, exit costs, and so on. Now, this observed behavior that we see, and this is very much like in static models where we say, what's the optimal price? It satisfies this first order condition. In dynamic models, the same thing holds. The observed behavior is again the solution to a maximization problem, except the big difference between static and dynamic models, and in some sense, in the estimation of dynamic models, this is going to be the entire difficulty. So here, the optimization problem that agents are solving depends not just on the profit function, the per period profit function, but also on the expected value function, basically. And this is the object that is going to give us a hard time empirically. Essentially, the methods that we're going to talk about are all going to be ways to essentially get around computing the expected discounted stream of profits, which of course depend on expectations, they depend on what my opponents are doing, and so on. To give a concrete example, let's take firm entry. Firm entry depends on how much I'm making every period, the per period profit function, but also on your expected future profitability, which in turn depends on the equilibrium strategies of all the firms in the market and whatever other states you might have that are moving over time. And so essentially, if you want to compute the implied entry costs, you see observed entry behavior, you need to be able to compute this expected discounted stream of profits. And so our entire discussion is essentially going to center around how we are going to do that. Okay? So if you're sort of thinking about, okay, we need to compute these value functions, the most intuitive thing that comes to your mind, and that's going to be our starting point, is, okay, why don't we just solve them? We've done macro problem sets, and we've solved value functions many, many times. What is the issue? Let's just solve for the equilibrium of the game, plug it in a GMM or maximum likelihood procedure, and get our parameters of interest. So what would an estimation procedure that did that look like? First of all, this would be, we would call this, and it is called, as a nested fixed point estimator. Why? Because you would essentially nest a fixed point, which would be the solution to the Bellman equation, into an estimation routine. So what's our goal? We want to recover some parameters of interest, for example, entry costs, exit costs, investment costs. Let's call it theta. So what would you do? You would say, guess a value for theta, compute the equilibrium of the game. We're going to get value functions which depend on the state and this particular guess that I had for parameters theta. Now use my sample and use this computed value function and plug this into some objective function. And a lot of this will become much clearer in a few minutes. But the idea would be solve the game, plug it into some objective function. And this could be sort of, let's match the observed to the model implied equilibrium policies. So match observed entry to sort of model implied entry into some moment conditions. And once you have these two steps, just iterate over theta. So give me a theta, compute the equilibrium of the game. Now you know the value functions. Once you know the value functions, write down the optimal policies, match them to the data. If it doesn't look good, update theta. Okay? Now, the really nice thing about this is that you would have, it's a full solution. So you would really be finding the value functions correctly with no error. But the problem is that this can be computationally difficult. And on top of that, you might have multiple equilibria. So this can be an unsurmountable problem. Both of these can be unsurmountable problems.
I don't really understand what's the conceptual difference between this kind of estimation and the calibration. In the sense that in both cases, we start with some, in both cases, it's kind of a method of moments, right? That we eventually...
What do you mean by calibration?
Okay, so a calibration exercise would be to choose theta until the moments of the model will match some moments in the data, right?
Well, that sounds like this.
Right. Okay.
So that's a... then I'm not entirely sure what you're asking. If you
no, I mean, so many times I've seen, I mean, maybe it's a terminology issue, but I mean, many times I've seen calibration exercise just meaning matching the resulted moments in the model. I mean, finding the right data to match the resulted moments in the model to moments in the data. Okay, but again, maybe it's just...
Go ahead.
Calibration is a weak form of that. The same thing, except for you don't worry about the properties of the estimate.
So when I talk with macro people, I joke that it's the same thing, you just don't have standard errors. It's kind of... No, but I think that's right. But what you described matches what I'm describing. And we will see in a lot more detail what is going on in here. Okay? So I want to start by actually talking about a nested fixed point estimator, because actually if you didn't have a game and you had a single agent problem, and we'll see actually some applications that are single agent because the markets are going to be almost perfectly competitive, this is how you would actually go about estimating the model. Because if you have a single agent problem, it is neither computationally difficult, usually, nor do you have the multiplicity problem, because you're going to have a contraction map here, and then boom, you're done. It's a very straightforward estimator. So before going into how you would go about things in the case of games, I want to go through the standard nested fixed point estimator. And I'm sure some people in the room are going to have seen this before. This goes back to Rust 87, which is sort of a seminal paper, proposes this estimator for single agent dynamic problems. And we're going to do this for a fairly simple class of models, which are called dynamic discrete choice, and they are exactly what you expect them to be. They think about a simple static logic model, except there is a future, and so for every choice there is a value function that you are trying to maximize. So here is a very fast overview of these models. So you have an agent. In each period, he's choosing some action A. You have a state S that the agent is controlling with this action A. In the case of Rust, the agent is Harold Zurcher, who was a mechanic at the Wisconsin Bus Authority, and he was deciding when to replace the engine of each bus. And he's going to get some payoff that depends on an action and a state. And just like in standard static discrete choice, there is going to be a shock epsilon, let's say it's logit, associated with each action in each period. And this is IID over time, so it's not a sort of real state. We have a state transition. There should be an action here, I'm sorry. So the state in this case is the mileage of the bus. So as the bus gets more and more used, you will be more and more likely essentially to replace the engine to avoid sort of very bad mechanical problems. Probabilistically, the state evolves according to today's state and today's action. So in Rust's case, as I was saying, you have a binary choice. You either keep the engine or you replace it, and S is the mileage of the bus. And what you want to estimate is essentially this payoff function theta. So imagine this payoff function as having some parameters like the replacement cost of an engine. This would be like a switching cost parameter, and then how much costs are changing with the mileage of the bus. So these are the parameters that we actually care about. So what would you do if this was a static problem? You would open stata. You would say, OK, I know how to do this. We know the agent's problem is to choose an action to maximize the payoff function plus epsilon. And you would just do maximum likelihood using the observed choices of when Harold is basically replacing the engines of the bus. But it's not a static problem. There are dynamics. And so the agent has a Bellman equation of this form. So he's choosing an action to maximize his current payoff. I'm sorry, I forgot the epsilons in all my equations. But it's a dynamic discrete choice problem. So he's choosing this discrete choice A, binary in this case, to maximize his per period payoff, plus his future value, so his expected value function tomorrow, at the state that will prevail tomorrow, given today's state and the action that he chose. Okay? So just like a static discrete choice model, except we have this term that we need to deal with. If epsilon are logit, we have no problem figuring out what the optimal policy is going to be. Okay? So what is the probability that you're going to choose a particular action A? You're going to have your standard logit formula. So without these terms, this is standard logit. But your utility is not just today's payoff. It is also your future, your continuation value. So in these logit formulas, these expected value functions are going to show up. And I'm showing this because it's showing you really clearly what is the issue with dynamic models. All right? If this was static, you would just do your logit maximum likelihood. But now you have this extra term that you actually have to deal with. Okay? And in all of the examples we're going to look at, this is going to be the entire difficulty of the problem. Okay? So what does Rust propose? He says, okay, I will still do a maximum likelihood here to estimate my parameters theta. And essentially, inside my likelihood, I'm going to solve for this value function, hence the nested fixed point algorithm. So he is going to say, give me a guess of theta. For this theta, let's solve for the value function. So use a standard fixed point algorithm. In principle, this is going to be fairly fast. Then take my sample, which consists of actions and states. So I know at each state what the agent did. And form the likelihood in a very straightforward manner. What's the likelihood? I'm computing basically at each time period where I was at a particular state st, what's the probability that I chose a particular action, and what's the probability that I reached this particular state. Okay? This is the core object of the likelihood. This has a logit form. So give me theta, solve for this. Once I know this, when I come to these choice probabilities, this is known. So this is just something that I know, and I can estimate theta directly. Okay? I just have to do this iteratively for different guesses of the parameter theta. Okay? Does this make sense? So this approach is fairly simple, and it has the big benefit that it's full solution. So you're really solving for the problem. We're going to see later on that when we talk about dynamic games, we will not be solving the game. We will not really be solving the game in the estimation. Okay. Okay. So why can't we do this when we have an oligopoly rather than a single agent problem? So it can be computationally burdensome to do this nested fixed point, and we have multiplicity of equilibria. So I don't know of anybody who has actually used this methodology in dynamic in industry with industry data. So it's not used. And again, the main difficulty we have to deal with in games is to precisely deal with the value function. So what has happened in the last 10 years or so, and this literature is inspired by some earlier work on single agent setups by Hodgson Miller, is that some two-step methodologies have come up that we're going to talk about that allow us to estimate dynamic games. What happens in these two-step methods? Okay. In the first step, you are basically getting a first stage estimate of value functions. Okay? And this is the step that we're going to have to talk about mostly because that's the tricky part. So first you're going to somehow, and I'll tell you how, get a first stage estimate of value functions. This will amount to basically getting estimates of policy functions and transition rules, and from there moving on to the value function. Once you have the value function, it's not hard to move on. Because once you have the value function, you can essentially use it to get the parameters of interest. So let's suppose this was your problem. If you knew V, this would be completely straightforward. I hope everybody agrees with that. It would be a straight up static maximum likelihood of the logit variety, because if this was known, this has a parametric form, and I'm done. I can just do maximum likelihood. So if I can give you some estimate of this V, then we're going to be done. We're just going to use basically first order conditions or conditions for the optimal policies and get the parameters of interest. So the whole point is going to be, let's do a first stage where we're going to get this. We're not going to solve for it. We're going to get a first stage estimate of this value function. Okay? So I'm going to discuss, hopefully I will have the time to go over both two papers by Yari Ben-Kard-Levin and Pekis Ostrowski and Berry. And the ideas, the intuitions in the two papers are actually fairly similar. So once we've talked about one, it will be easy to talk about the other one. Okay, so let me start with BBL. So let me give you, so BBL is going to be this type of two-step estimator And let me give you an overview of what the two steps are doing. Okay? So the first step, as I said, is aimed at getting this estimate for the value function. How are we going to do this? Basically, what we're going to do is estimate policy functions and state transitions. Okay? And notice that these two objects are essentially right in our data, because we essentially see actions and we see what firms are choosing at different states. So essentially, your choice at each state is in our data, and the transition of states is in our data. Okay? That's going to be simple. We are basically going to imagine saying, okay, I know what you're choosing at each state. Your policy function is some function action alpha star for given S. This is something that I observe in my data. We can just do a regression. Same thing for state transitions. And so I can essentially obtain non-parametric estimates of state transitions and policy functions. And I'll explain all of this in detail. Then they're going to say, okay, actually, if I know the policy function and if I know the transition rule, I can simulate forward and, given some parameters, create paths of play. And once I have paths of play, I can compute the expected discounted stream of profits conditional on some parameter, which is actually the value function. Okay? And this way, they are going to get an estimate of the value function. Once they have that, essentially they are done, because they're going to come to the second stage to recover the structural parameters, and they're going to say now, standard I/O idea, we're going to impose that observed policies are obey equilibrium play, and based on that, knowing the value function, we are going to obtain the parameters of interest. Okay? So what I'm going to do is set up the model just as a quick reminder, and then go through each of these steps in detail. Yeah?
How these estimated value functions relate to the value functions we were computing, like in the previous example? Like what's the difference? Will there be convergence?
Ideally, there isn't one, but of course there's going to be error. So the previous method has the big advantage that you are solving for the value function. Now we're not. There's going to be sampling error in the value function. So let's come back to this once we've seen.
But you don't observe all the variants for the value functions, because you don't have all the values of the state variable.
Exactly. Exactly. So actually, there are a lot of important choices to make when you are at this point. I'll talk about it. But flexibility is important because we are going to extrapolate, for example, and rich data is going to be crucial to do this right. Okay. I'm going to come to a lot of this, and then feel free to interrupt me again. Okay, so let's do a quick recap of the model. So time is discrete, horizon is infinite. There is going to be n firms in the market that can change over time. And at time t, conditions are summarized by a state st. So just like yesterday, think of this st as having the state that each of these n firms have this particular period. What firms are going to do is, given this state, they're going to simultaneously choose an action. And actually, in this paper, the action can be discrete or continuous. So imagine the sort of benchmark model they look at is entry, exit, and investment, just like yesterday. So firms are choosing actions, alpha IT, the action profile for each firm looks like this. And then the state transition says that essentially we're moving to some state st plus 1 given st and what every firm is choosing today.
And epsilon, or
I'm sorry?
is there an error there?
Well, that's a probability.
Yeah.
So, okay. So, just like yesterday, before choosing an action, I'm just doing it slightly more generally. Before choosing an action, a firm is going to observe a private shock nu IT. This shock is going to be IID, and it is drawn from some distribution G that can depend on the state. So again, this is going to be the entry cost or the scrap value or some investment cost that like we saw yesterday. And then a firm every period gets a pay of pi that depends on everybody's actions, the state, and then these shocks. So imagine that this might have inside the entry cost and the scrap value that you pay if you decide to enter or exit. The firm chooses these actions to basically maximize the expected discounted stream of profits. Okay, and again, expectations are basically over the future state variables, the future values of the private shocks for itself and for every other firm in the market. Okay? We're going to look at Markov perfect equilibria. So a strategy in this case for firm I is going to be a function that takes us from the state and the shock that I saw. Again, these are private, NIID, just like yesterday. So given the state and given a shock that I observed today, I'm going to choose an action according to the strategy sigma. Okay? And a strategy profile sigma for which has the strategy of each firm is a Markov perfect equilibrium if for all states and all other strategies sigma prime, the value of following sigma given sigma minus I is larger than the value of following any other strategy against sigma minus I. Okay, what's the value? Essentially, it's our standard value function. It's your profit today plus your expected value tomorrow. So I'm taking expectation over the state tomorrow and my shock tomorrow, which I don't see. So I'm integrating over my shock tomorrow as well as the aggregate state of the industry tomorrow, given the strategy profile sigma that is followed by all the firms. And notice that I'm also integrating over the shocks of the other guys because today I don't know the shocks that everybody else saw. So I can only predict what their behavior is going to be given sigma. Okay? Anyway, these are the important inequalities which are standard to look at.
Just in case you are expecting over the other player's shocks, but also your future shocks.
That's here. That's here.
Oh, I see. Okay.
Yeah. It's just that today I also don't know what your shock is going to be. At the end of the day, very often in the applied models, we have a slightly simpler version of pi that doesn't depend on everybody's action, but only on... So for example, yesterday, our pi was pi of omega, not pi of omega and the action profile. Imagine sort of a time to build period. It takes us a period for our actions to be implemented, and we only care about omega. But here, we're allowing for it. It's fine. There's no problem in doing it. You just have to take this additional expectation. Okay. So to sort of sum it up, in each period, firms wake up, they observe the state of the industry S. Each firm I draws a private shock nu IT from the distribution G. It chooses an action alpha IT. It earns its profit, and the state evolves according to the transition rule, P, the probability of future states given current states and actions. Okay. Okay, so this is our model. What are the structural parameters that we actually want to get? Okay. So first of all, we have the per period profit functions. Okay, so again, this is going to be some sort of Cournot or differentiated Bertrand game as an example. We are interested in the shock distributions G. So these are going to be the entry cost and the scrap value distributions, just like yesterday. The transition P, and then finally the discount factor beta. All right? So we usually assume that beta is known. And the reason is that we know, even from single agent setups, that we cannot actually identify beta. Okay? So usually what people are going to do is set this beta equal to something based on the quarterly interest rate or something like that. And it's also worth noting that this part, if you look at it, and I'll come back to this, is something that's observable. Because all it's doing is, you know states, you know actions. So given a certain action profile and a state today, you know in the data how likely you are to go to every other state. Okay, so this is something that you can actually read off of the data. So the parameters that we are going to focus on are these two. But then, as I was also mentioning yesterday, we often are able to get these profits offline. So again, if every period you have a static quantity or price game, this is something that you can use standard methodologies to get at, like BLP or standard Cournot. And so in this case, you would not worry about these two. This leaves us with the core parameters we are interested in, dynamics, these shock distributions G. So this is basically entry cost, scrap value, and investment costs. And these are the core parameters that I'm going to talk about. Of course, if you had learning by doing, there would be parameters in here that would become dynamic. So if this is something like revenue minus costs, revenue is usually easy because it's just coming from demand. Costs, if it's static, we can do BLP. If it's not, it's going to become a dynamic parameter because if your quantity tomorrow affects your costs, the value function comes in. Okay. Now, the data, which again is actions and states, can come from one market or it can come from multiple markets. We're going to see the actions that people are choosing and the states at which they're choosing these actions, and possibly the sort of profits, so prices, quantities, demand shifter, cost shifters. Now, one assumption that is important here is that we're going to assume that for each market, the data is generated by a single equilibrium. Okay? And this assumption, if you have a unique equilibrium, is fine, but if you don't, it can be problematic. And there is actually some work that has looked at whether this can be a problem in certain applications and what it means. So what would it mean if you were pulling data from two markets where different equilibria are played, but you were assuming it's the same equilibria? What is it that you are actually estimating? Okay, but we're not going to think about this today. We're going to assume that the policy functions are the same across these markets. You can condition on market characteristics, like market size. That can be a state, but here we're going to do that. Okay, so here are the two steps. So now we can get into them. So the first step is going to basically estimate two objects and compute a third. So we're going to estimate the transition, so probability of going to S prime given S and A, and the policy function, so the function sigma of the state and the shock nu. Okay? And then once we have these two objects, we're going to use a forward simulation procedure to compute the value functions. Okay? And then in the second step, we're going to impose equilibrium conditions to actually get the parameters that we are interested in. So let's look at these two steps. And I hope you'll see where all the choices and the different issues come in. So the first step is to recover the state transition function. What's the state transition function? It is basically a function that takes us from an action and a state to probabilities over the state. Okay? And as I was saying before, this is something that is observed. Okay? So we can directly measure how many times we transition from a particular state and an action to another state. Okay? So it's yeah. So I wish there was a little bit more board space. So suppose that you have three states, right? What you want to obtain is basically, you have three states. What you want to get is basically a matrix that tells you what's the probability you go from.
No, I mean this I know. I mean example of like a market and what do you mean by we observe state in action?
Oh.
What kind of states are there in a market?
Well, it's just like we were saying yesterday. So, for example, it could be that we care about the distribution of capital, and we see firms investing, right? So then that's a fairly simple example. Then you might say it's a deterministic transition.
You observe capital.
And you observe capital.
Okay.
Okay? Another state might actually might be exogenous. So one state you might care about is the demand. So that's the simplest example I could give you. So imagine you have market size as a state variable. Right? That's exogenous. And so you just say, okay, I'm going to take market size, let's say population. Might not be a good idea, but that's one example. And it's an AR1. And so I just estimate an AR1. That's a very simple example. In other cases, it will depend on the action. It will be how, some examples are very hard. So if you want to estimate how an entire distribution of product qualities evolves, that's a hard one because it's going to be a very large dimensional object and it might be complicated to get at it right. It might move very slowly. Some other states might exhibit non-stationarity, so then it's going to become complicated to get it right and so on and so forth. Which brings me to this point, which is that I can tell you that this is off of the data. In practice, it's a bit of an art to get this to work. And it's really a choice between, it's very application specific because it depends a lot on what the data is and how rich it is and how long the time series is. And it's really a choice about essentially flexibility and feasibility. So you want to be very flexible, and I'll tell you why in a second, but it has to be feasible. So ideally, you would want to do this completely non-parametrically. Of course, so suppose you want to get this I don't know. They're kind of hidden. How do they? You might want to get, so given an action, you might want to get what's the probability of going from S1 to S1, from S1 to S2, from S1 to S3. If you have non-stationary situations, you might see data only on one direction along this matrix, and so you just can't go non-parametric because you'll just have you won't have data on a lot of these cells. So it becomes so in principle, this is in your data. In practice, you have to think hard about being flexible versus being doing something feasible. Does that make sense? Okay. The second example is the second step of the first step is to estimate the optimal policy. Okay, and this one I think will bring to light what I was saying before even more. So what is the first stage estimate of the policies that firms are following? What's the optimal policy? It's a function that is taking us from the state and the shock to an action. Okay, so if you forget for a second the shock, suppose that we didn't have these IID shocks, the policy function would just take you from a state to an action. Okay, so take the capital example. Oh no, I put it in there. Okay, so take the capital example I gave before. What the policy function would be is it would say, what's my optimal investment when my capital stock is K? And of course, this is for me. And then let's denote the distribution of K by K bar. Okay? And no shocks for a second. Then, in principle, and we could discuss that, I could run a regression. I could run a very flexible regression here. And I could tell you, when the state is this, what this firm is going to use. Okay? If it was a discrete choice, do I replace the engine or not, or do I enter or not, let's say entry, you would say, what is the probability of entry? It's a function of the state, which might be, let's say, just the number of firms. Suppose firms were homogeneous and it was just entry and exit. And here I am doing a probit of the number of firms, or entry probabilities on the number of firms, right? And so this would be entirely straightforward. I can really read an estimate off of the data, okay? Now, this is more complex, but it's going to be the same idea because we have these shocks new. So in principle, this function sigma is a very complicated object because remember, it's the solution to the Bellman equation, And here I'm telling you, yes, but forget about that. I can actually see in the data what people are using at different states. And so I can get a sense of what these actions are at the different states of the world just off of the data, ignoring the underlying structure of the value function. Okay? So now again, how you do this in practice is going to be application specific, and it's going to differ on based whether you have a discrete choice or a continuous choice. So BBL will discuss both. So discrete choice, this is inspired by Hodge and Miller. I don't have time to talk about it, but that's another classic paper. You'll see, though, it's a very similar idea. They also talk about continuous choice when the strategy is increasing in the shock. So imagine you have investment, and this is a cost shock to investment. So let me talk about only the first case today. Again, you have the same trade-off. You want flexibility, and here it's even more important than the policy, than the transition rule. But flexibility can be difficult if you have a large state space. Now, why do I say that flexibility is important here? Because if I go and impose, take the investment example. Suppose I did a linear regression here, right? Remember that the optimal policy is a very complicated object resulting from this dynamic problem. If I go and do something very simple here that's linear, I can be very wrong. And remember that I'm going to use this, well, I haven't told you yet, but you'll see that I'm going to use this to construct value functions. I'm going to extrapolate using this. I need something very, very flexible, precisely because it is capturing a very rich underlying problem. So it's important here not to do something overly parametric or overly restrictive. Yeah?
So in the model, we assume that the policy is only a function of the state, right? So do we require in this kind of estimation a high R-squared, for example?
Yeah, that's a good question. Yes, you would. That's exactly right. So if this thing performs poorly, it's like saying that you are ignoring variables that are very important to the firm. So this is, you're exactly right that this is a sort of prediction exercise. And you'll see, because I'm going to do a forward simulation, all I want at this stage is to be able to predict what people are going to do. That's all I want. And actually, we don't have time to talk about this, but I'm telling you to run these regressions. In principle, your econometrics one self should say, these are very problematic. If you start running, for example, number of firms on market size as a state variable, you'd better start thinking about instruments. And precisely because for now we are only thinking about prediction, we're not going to worry about it. Although there is some very recent work saying that maybe we should, and maybe there are corrections here for this type of problems. Okay, so let me give you the discrete choice, which is also a window into the Hodge-Miller idea. So I'll walk you through this because the notation is a little heavy. So let's go back to our Rust example, okay? So my per period payoff is basically of the logit variety. So it has a payoff that depends on the action in the state plus these epsilons, these nus, which are like logit shocks, okay? Okay, that's my model. So let's define the choice-specific value function as small v. What is small v, the conditional value function, the choice-specific value function? It is basically the money I'm going to make if I choose action A today. So forget this for a second. Well, actually, you know what? It's going to be simpler to tell you here. If my value function is max over pi plus epsilon plus beta expected v, I'm killing the notation, but if it's something like this, then basically the value function conditional on action A is going to be the profit plus beta expected v. Okay? So it's everything in here other than epsilon. It's the money I expect to make from today and forever after if I choose action A. Okay? That's what Hodge-Miller called the conditional value function. So that's exactly what I've written up here. I just have all the integrals. So basically it's your payoff. Again, I need to predict what others are going to do, so it's not as simple as there, plus my expected value function. Okay? Now, what's happening? What is the agent doing? If you look at it from here, when does the agent choose action A? He's choosing action A such that this plus epsilon is the max, right? Just because this thing is just profit plus expected value function. So what's your optimal policy? Your optimal policy is going to be choose action A if and only if the money you expect to make from A, from today and forever after, plus the shock is larger than any other action.
Does the shock depend on the action?
We'll think of it as logic. So I'm choosing cars and I have a different epsilon for each car. That's all. It's just weird notation. It's just not the standard way to write it. Okay? So now watch this. Okay? And it's actually very simple. It's extremely simple. What's the optimal policy? All right? To figure out the optimal policy, all you need to know is differences of these conditional value functions. Just like in static models, what you need is utility differences, except now we're not in a static model, so I don't want just the per period utility differences. I want differences of these more complicated objects, which are the conditional value functions. Okay? So now, what Hodge and Miller are going to notice, and this goes again back to static discrete choice in some sense, is that differences in conditional value functions are actually observed because they are just differences in log conditional choice probabilities. Okay? So if you're familiar with the Berry inversion, this is identical. It's saying that deltas, the mean utilities, are differences in market shares. It's exactly the same thing, except mean utilities are now these conditional value functions. Okay? So it would just be, what's the probability of choosing A? It's logit like it's exponential VA over some exponential over J. Now take alpha prime, take the ratio, denominator goes away, difference of the numerator, and that's the differences in conditional value functions. Okay? Does that make sense? Now revert the argument to do the empirical version. I see conditional choice probabilities because this is data. This is just with what probabilities are people choosing actions, which means I know differences in value functions. And that's enough to know the optimal policy. Because if at every state I know differences of value functions, I can tell you what the agent is going to do. So give me an epsilon, give me a nu, tell me what it is. Tell me that nu today is 1, all right? If I know this, I know what the agent is going to do. And so I can essentially predict what these guys are going to do just by knowing the observed CCPs. Okay? Again, if I didn't have the news, I would just be doing probits and regressions. And in practice, people do that a lot. They sort of forget about that. But if I want to take the news seriously, I go to Hodge and Miller, and I predict what people are going to do this way. Does that make sense? Yeah?
Where goes the distributional assumption over the
Right. So here I'm doing, this is logit.
But that's what so at some point you said you wanted to get exactly that distribution. Because you thought that was about getting across this.
You're completely right. So in this example, you're completely right. So in this example, which is a dynamic discrete, goes back to the dynamic discrete choice, imagine that the parameters of interest are in here, in the profit function, and not in these logit shocks. So it could be switching costs it could be that your switching cost is basically some theta plus epsilon. And you impose something on epsilon, but you still get theta. In the dynamic entry models, usually, and you will see it in the applications in a few minutes, what people will do is forget about this and say, let's run a probit for entry on the state and move on. Okay, but I wanted to, this was an excuse to also talk about Hodge and Miller a little bit. So it's a lot of material, but I hope that through the applications you can get at least all the main ideas that are hidden in here. Okay, so now this part is sort of straightforward. So we have the policy functions. We have the state transition rules. How are we going to get the value function? Okay. What's the value function? The value function is simply the infinite discounted stream of profits. Okay. So, and in this infinite discounted stream of profits, we're integrating over the shocks and predicting and using the state transitions. And there are some parameters theta that we care about both through the profit and the distributions G. So the idea is going to be to essentially simulate these value functions under the estimated policy and transition rule that we just found. So what's the idea? Okay. So give me the observed strategy policies, the observed optimal policy that I estimated sigma, and give me a guess of the parameters theta. Okay. Now let's start at a particular state S0. Draw shocks from the distributions G, which I have my guess theta for. For this S0 and shock nu 0, I can compute the action profile. So I can compute the action of each firm since I've estimated this function. And I can compute, given theta, the payoff that each firm got in this particular state. Now use the estimated transition to draw an S1 given S0 and the action profile that firms chose. And keep doing this. Okay? So basically what you would do is start from an S0. At S0, draw a new 0. Tell me what these guys are going to do, right, of S0. Now, from here, I can draw an S1 from this probability that I actually estimated. Give me a second. Go to S1. At S1, draw another new. Tell me what people are going to do. Draw an S2. And create a path of play. Then, at each of these S, given theta, I can compute the profits. Right? And then I can say, okay, let's just do the infinite discounted sum. Do this many, many times, take the average, and that's an estimate of your value function. Okay? And now notice that I can do this not just for the estimated sigma, I can do this for any sigma. Okay? I can perturb sigma to some sigma prime and compute the value under some deviation or some alternative strategy. Okay? Yeah.
About the previous point, about this very thing. So in discrete choice, I usually think that I choose stuff only to maximize my utility and then not strategic, and so discrete choice makes a lot of sense in a non-strategic context. But here, the actions are strategic, right?
Right. So all I meant was that algebraically, this is Berry's inversion. It's just saying, but these are complicated objects that depend on future play. But I don't care. All I want is to compute differences of these things.
Yeah.
Right? So this is not your static payoff or some delta like in Berry. This is a conditional value function, which is basically your profit today, which depends on what people are doing, plus your expected value tomorrow, which depends on what people are doing. But for me, all that matters is to get non-parametrically differences of these things. Because I'm not getting structural parameters here. I'm only computing differences in CCPs, because once I have these numbers of these differences at each state, I can tell you what they're going to do. Because they're going to look at these numbers, they're going to look at epsilon, and they will choose an action accordingly. Right? I'm not obtaining anything structural. It's only a first stage estimate of thresholds of when people choose one thing versus another. Does that make sense?
Yeah, makes sense. It feels like you're tricking me a bit, but
I know. The first time it feels that way, but it's true.
So it seems that this process of simulating is very sensitive to what big G distribution is. So where are we getting it, and how we can be sure that it's kind of
Right.
converges as you go through simulation?
Right, that's a good question, and it's hard to know the answer. So people will usually say entry costs are log normal, and we are going to estimate the parameters. And to be honest, in everything I've worked on, I've never found the parametric assumption to matter very much. But it's hard to know. It's an empirical question of robustness in some sense. And I don't think people have looked at non-parametric. I could be wrong, but I don't think people have looked at non-parametric estimation of these distributions.
And econometric properties.
People have looked at, though, in dynamic discrete choice, actually, non-parametric distributions of the epsilon. So sort of if it's not logit, so Aureo de Paula has some work on this, but for single agent setups. Okay. So that's it. So this way I'm forward simulating, getting a value function. Once I have the value function, I am done with stage 1, and I'm going to move to stage 2. What is stage 2? And I'm only going to give you a very brief one slide here, and then I think I'm going to try to show you more of this in applications. You're going to do something like the following. So stage 2, think of it as a standard I/O estimation methodology of taking equilibrium conditions and matching those to the data. So in the second stage, we are basically going to say that what's a Markov perfect equilibrium? It has to be that the value under the observed policy sigma is higher against sigma minus I than following any other strategy sigma I prime. So what we're going to do is we're going to compute the value under all strategies sigma prime and ask that these inequalities hold. So we're essentially going to look for the parameters theta such that the parameters theta, strategy sigma, and transitions satisfy these inequalities for every firm, every state, and every possible deviation. Okay? Now, there is discussion about the second stage. This can be tricky because what does it mean to do this for all sigma prime? In practice, this sounds very complex. And people have done things in practice like perturb slightly the observed policy or do one-shot deviations. The truth is, and you will see in all the applications I'm going to talk about are not going to use this second stage, actually. But you can go back to the Rust idea of, sort of Rust idea anyway, of saying I'm not going to ask for these inequalities to hold. I'm simply going to, and that's an alternative, I'm simply going to match observed and equilibrium choices, right? So just like in the discrete choice world, you would have said, now I computed V by my forward simulation. Now I know the optimal policy looks like this. I want to get theta. I am just going to do maximum likelihood or method of moments where I'm going to say this is data. I already used it in the first stage. But now I am not going to do some, first stage prediction exercise. I'm going to impose equilibrium, and I'm going to say these actions that we see need to obey this optimal behavior. And now I have a simulated version of this value function. So I know this thing. I don't need to worry about it. I can just get theta. Okay, and that's an alternative for the second step. Okay? Okay. So, okay, good. I thought I had another technical thing. Good. So let me briefly illustrate some of this with an application. So this was a job market paper from 2006, if I'm not mistaken. And I think it was the first paper to apply BBL. So what does this paper do? It's an environmental paper, and it basically measures the welfare costs of the 1990 Clean Air Act amendments on the US Portland cement industry. So you know there is a lot of papers on sort of cement and so on. Turns out it's actually one of the biggest polluting industries in the US. And so we are going to basically look at how an environmental policy, beyond the environmental impact it has, also changes the market structure of an industry and what are the associated welfare implications. So typically, a cost analysis of this type of policy is sort of an engineering estimate of how much it's going to cost to bring all the firms up to date and bring new plants into compliance. But this type of cost analysis, he argues, is going to miss several relevant economic issues that are relevant in concentrated industries and that he actually wants to address through this dynamic model. So he's going to say that basically there are, in industries where there are large sunk entry costs and costly investment, these are going to determine market structure. And when a policy affects these type of parameters, you're essentially going to change market structure. You're going to possibly be led to a market with fewer firms, lower production, increase in market concentration, and so there are going to be welfare implications over and above what happens to environment. So what he's going to do is, and I'm going to try and give you a sort of overview of how, again, how the Ericsson-Pekes model is used and the BBL estimation approach is used. So he's going to do this methodology on the cement industry. He's going to have spatially segregated regional markets. So if you've seen the Syverson papers, you already know this. These are industries where transportation costs are really large, and so you can't really transport cement very far, and markets tend to be spatially segregated. The state here, the relevant state, is going to be a firm's capacity. And actually, the reason I like talking about this paper is that it's an excuse to talk about some interesting investment and capacity patterns. So that's my main interest here. So firms have a capacity which they can invest to increase or decrease. What happens every period? Firms are going to play Cournot. So there's going to be a market demand, and firms are going to choose how much to produce, but they're going to be capacity constrained. Okay? And that's an interesting empirical question already of how do you estimate a cost function under capacity constraints when they're not really strict, because really measuring capacity is really hard because you're really asking the firm what's the max you can produce. And unless you're looking at steel producers where you're asking them to tell you in a time of war how much output can you have, it's actually it's actually something that is tough to measure, and a lot of the measures are not as reliable as we think it is, as we think they are. And so he's going to think about a cost function that is sort of hockey stick and try to understand where the hockey stick kicks in the data at what point. Anyway, the firms are going to choose to invest in capacity as well as entry and exit. And production is going to be static, so we're not going to think about it. It's going to come off of the per period payoff. Markets evolve with firm entry and exit and capacity adjustments. And when the environmental policy is going to kick in, all these policies are going to change the market structure of these firms. So what he's going to do is basically use the BBL procedure to estimate the investment cost, the entry and the exit cost before and after the amendments. Okay? And then finally compute the welfare costs. So as I said, what I think is really interesting in this paper is the investment aspect in capacity. And so what he sees in the data, which is very common, and macroeconomists have thought a lot about this, is the empirical regularity that investment tends to be very lumpy. Okay? So firms will not invest, not invest, not invest, not invest, not invest, invest, not invest, not invest, not invest. And this is just something that becomes hard to explain. If you think about the first stage policy we were talking about before, where I would get investment as a function of capital, it's hard to estimate it because nothing would happen and then you would have a jump and then nothing will happen and you have a jump and so on and so forth, which means that really there is an underlying model of adjustment costs that you need to get at that is not empirically straightforward to get at. So indeed, these firms make adjustments, do not make adjustments in most periods. The model adjustment is 0, and essentially they make infrequent, often large capacity adjustments. Okay? So you have these jumps in market level capacity, both because of this investment process and also through investment entry and exit. So how is he going to capture this empirical pattern? And these are some of the core parameters he wants to estimate. So the core parameters are basically the investment cost function. And what he's going to say is, so if investment is X, he's going to say that the investment cost looks like this. He's going to say, okay, you can invest or you can divest, okay? And either way, you're going to have convex costs, okay? And you're going to have fixed costs. And this sort of functional form possibly has the ability to give you this pattern in the data because you have to overcome the fixed costs and decide to invest, and then the convexity is also going to kick in. So fixed costs are going to be setup costs such as getting permits or constructing support facilities regardless of the size of your current kiln, which is the main capital equipment these factories use. And then the convexity, the parameters gamma, are going to capture the actual level of investment once you decide to invest. So these will capture the zeros, and these parameters will capture the actual amount of investment that we see. He also allows for divestment. This goes back to a question we had yesterday. You have divestment sunk cost that may be positive because it might actually be costly for you to dispose of the kiln. But of course, they could also be positive because you could sell off part of your capital equipment. Now, what's interesting, first overview of what he's going to do. So these are the 2 BBL steps. First step is going to be the following. Per period payoff first, okay? So he's going to get a demand curve for cement and estimate production costs. This is standard static Cournot. So, well, this is standard market demand curve. This is almost standard Cournot, first order, get marginal cost from first order conditions, except for the capacity constraints, which have this hockey stick, and you need to estimate the curvature of the cost function. And that can be tricky. Then he's going to use to estimate the first stage policy function for investment. And this is sort of the interesting part of the paper, because as we were just saying, you're not going to be able to just regress investment on your current capacity. It's going to look really bad. So what he's going to do is use an assess rule and basically estimate the bound. So what's an assess rule? The assess says that basically there are some thresholds. You want to achieve an optimal capital or capacity. If you are within this range, you don't do anything because of adjustment costs. Once you exit this range, you are going to adjust, and you're going to. So if you reach this capital level, you will adjust and you will go to the optimal one. So what does it mean to estimate a first stage assess rule? It means non-parametric estimates of this, and this. Okay? And it turns out that you can actually get this straight off of them data. Okay? So that's going to be his first stage policy function. And then the entry and exit policy functions are simple. He's just going to do products. Second step of BB, and then he's going to simulate the value function. And then the second step, he's going to use the moments that we just saw, the inequalities that define MPE. And he's going to estimate his main primitives, which are the entry exit costs. and all of these parameters in the investment cost function. So this is a very brief overview of the paper. What are the main findings? He's basically going to look at the impact of the Cleaner Act amendments, and he's going to look at before and after the regulations, expected producer and consumer welfare, market structure, so number and size of firms, distribution of cost across incumbents and potential entrants, and to some extent disappointingly, but I don't know what more he could have done, we're not going to think about the actual environmental aspect of this. Okay? He finds that overall product market welfare decreased quite substantially, and most of it is going to come through entry, because it turns out the amendments massively increased the sunk entry costs for firms, because they made it very hard for you to open a new plant. You basically had to undergo very severe checks and regulations, and you had to meet a lot of standards. On the other hand, incumbents do not seem to be affected too much by what happened. Finally, if we were doing this statically, you would not be accounting for a lot of the entry patterns, and your numbers would be way off.
And the reason why the fact that entry is so much more expensive is bad for consumers is that the existing firms are behaving more monopolistically?
So
Why do we care about entry?
I suspect a lot of it comes from the actual entry costs that were paid by the firms, which became a lot higher.
These are firms that actually did entry.
Right, right, and they would not have. So on one hand, and exactly, and we would be led to a much more concentrated market. Exactly.
And how does this decline in welfare compare with the old-fashioned computation where you're just looking at engineering costs?
He has those numbers. To be honest, I don't remember them. But he actually is making a comparison.
Are these a lot larger than the...
That's a good question. I don't remember. But he actually does make the point.
Isn't this the last bullet?
Hmm?
Isn't this the last bullet?
No, this is static analysis, not the engineering estimate. Okay. Okay, so I'm not doing great in terms of timing. So I am going to keep talking about applications. I'm going to talk about, given the time, probably one more empirical paper. And, okay, we'll see. Maybe if I have time, I'll come back to it at lecture 3. Okay, so I want to give you, this was my PhD, and it's using all of these methodologies. And the goal was to look at industries with cycles. So what happens in industries that you have severe sort of boom and bust cycles? What is the nature of fluctuations and cyclicality? And in particular, how does uncertainty about the future and investment adjustment costs, much like what we just saw in Stephen Ryan's paper, affect the volatility in a given market? We're going to look at a particular example, and I'll show you some graphs, which is the world bulk shipping industry. And then we'll talk again about it after lunch. So what is bulk shipping? Bulk shipping concerns ships that are designed to carry a homogeneous, unpacked, dry cargo for individual shippers on non-scheduled routes. So we'll come back to this after lunch, but basically think about these firms as taxi drivers. So these are ships. They meet an exporter, they carry his product from point A to point B, then they're going to meet another firm. So basically the entire cargo in a particular trip will belong to one exporter. And bulk shipping is fairly large in terms of tonnage. It's about 70% of trade and maybe 30% of value. Okay? We're talking about goods that are mostly raw materials such as iron ore, grain, coal, steel, wood chips, and things like that. So they're bulk. You basically fill up the whole ship and it goes from point A to point B. So this market is very volatile. In fact, it's probably 3 or 4 times more volatile than the US stock market. You may be familiar with the so-called BFI. So this is the Baltic Dry Index. which is basically an average of spot prices to hire a ship to transport your goods. And what you can see here is basically the substantial volatility that these prices exhibit. So between about the early 2000s and 2008, we see that basically these prices with some up and downs went up about 8-fold. And this is partly driven because China in this time period is growing dramatically. And in this case, China is importing a lot of raw materials because it's building infrastructure, roads, cities, and so on. So prices shoot up. And then in 2008, in the crisis, you had a collapse of these prices that was of historical magnitude. Okay? Now, at the same time as this time period, you had an investment boom. Okay? So, which is not unique to this decade. This, for centuries, has been the history of this market. This is the total backlog of these ships. So it's basically the total number of ships that are under construction at any given point in time. And you can see that in the same period, you have about an 8 or 9-fold increase in this backlog. Okay? Now notice that this is where the crisis hits. This is at a point of sort of a really high investment in these types of ships. And right here when the crisis hit, of course the industry was hit with a massive shock. So this picture is basically showing the number of ships. This is outside of Singapore. It's the biggest gathering of ships in history, lying at anchor with no crew, cargo, or destination. And the really fascinating thing about it is not that these ships are out there sitting in the water, but this is 2009. In 2009, there was another 70% of the fleet under construction, and it was being delivered until about 2015 to 2016. Okay, so it was really a sort of dramatic situation for the crisis to hit at that point. So what I do in this paper is basically construct a dynamic model of ship entry and exit. And so we didn't see POB. Partly I skipped it because you get to see it here. It's essentially the same model. And the key features of this model is going to be that demand for sea transport is uncertain and volatile. And at the same time, supply adjusts very sluggishly because you have time to build. And time to build is not just the actual construction, which is about 2 years, but it's also cyclical. So when people invest, they all invest at the same time, and you end up having to wait even more than the standard construction time. There are entry costs, and then there are convex operating costs. So basically, ships cannot just do infinite number of trips in a particular month. Okay? And then what's going to be a little different from the standard methods that we just saw is that basically I will have a data set of second-hand ship sales, which is going to give me the prices at which ship owners are selling the ships to each other. And these prices, I'm basically going to use them to get a direct insight onto the value functions. Because these prices are going to act as a measure of what your expected discounted stream of profits are forever into the future. And so instead of forward simulating value functions, I'm going to use this data to basically get at the dynamics of interest. Okay? So let me go through the model. So the model is going to be very simple, and again, it's basically the same as Pekes-Ostrovsky-Berry. So constant returns to scale. We're going to assume that the ship is a firm. So if you have 5 ships, you make 5 times the profit. And there's going to be 2 types of agents, like in all the methods that we saw. So there's going to be a number of incumbents. Think of this number as fairly large, in the order of thousands, or in the order of thousands. And then there is going to be a large number of potential entrants. And it's an excuse to also show you a different entry model. And it's going to simply be entry and exit decisions by these firms. The state variable is going to include an individual state, which is going to be the age of the ship. So as the ship gets older, its operation deteriorates and its costs increases. Since I care about my own age, I care about the distribution of ages. So in Ericsson-Pekes, this was my omega. This was the distribution over omegas. And so I care how many ships are 1-year-old, 2-year-old, 3-year-old, and so on.
Just a quick question. We should think of there being a global market for
Yes.
shipping services, so
Yes.
it doesn't subdivide
No, not at all. We'll see this in the next lecture, but ships tend to go everywhere in the world, basically. Did you?
Why do the intuition of like taking each ship as a film and not like film with a couple of ships?
It's an assumption. It's an assumption that I think makes sense in the sense that operationally, I don't think it's far from truth to say that there are constant returns to scale. That you have 3 ships, you make 3 times the profit. There can be things regarding risk, like long-term versus spot contracting and things like that. But other than that, there's not too much that. And by the way, also, probably half the owners do have 1 ship. So the largest guy has 3% of the fleet. So these are very small. Well, I guess the question is whether there are economies of scale in how you operate. So maybe, for example, you have, if you...
I can like manage my lines better if I know that I have like a reservation for China next month, so I can take...
Well, we'll see that in the next hour. These spot contracts are it's a very short-term market. So you book your contracts 6 days before loading, more or less. So, but it could be that with more ships, you might hire your own broker, for example. And then instead of going to instead of outsourcing. But I think to a first degree, it actually makes sense. Okay, so the aggregate state is also going to include the total backlog. So there's time to build, and that's what I'm looking at here. So this is basically how many ships will be delivered tomorrow, the day after, the day after, the day after, and so on and so forth. And then finally, and crucially, this is where the uncertainty and volatility are going to kick in, aggregate demand for shipping services. So think of this as the macro fluctuation, China growing, crisis, and so on. So what happens every period? Incumbents and potential entrants observe the state, so the age distribution, the backlog, and the demand. Then there's going to be a step that we haven't seen before, and we don't really need it from a model perspective. We're only going to use it in empirics, but I'm gonna mention it here, which is that a ship can be sold in the second-hand market if some exogenous liquidity shock of some kind hits the ship owner. So what's going to happen here? For us, a firm is a ship, and so a resale is not entry, the ship was already in operation, and it's not exit, because the ship will continue in operation. And because we're in this world of many small owners, the identity of the owner doesn't really matter. So when I'm selling my ship to you, the market structure remains unchanged. All I care about is the ship age and the distribution, which remains unchanged, right? So in this very simple non-model, there is a large number of identical buyers. And so if I think I'm making $50 million from this ship, you are also thinking that you're making $50 million for this ship. And so we're going to exchange the ship at basically $50 million. Okay? So this is a very simple way to say that under these assumptions, resale prices are going to essentially tell us what the value functions of these ships are. Okay? But model-wise, they're not doing anything. Then incumbents are going to privately observe scrap values. Think of this as the steel you get if your ship is dismantled in Bangladesh. And they decide whether they want to exit or continue. And at the same time, a free entry condition determines the number of entrants. Okay? Incumbents receive their operating profits, and then finally entry and exit decisions are implemented and the state evolves. Okay? What happens every
But you're
period?
saying there's no exit.
There is exit if you actually scrap the ship.
And does that happen?
Very little. I will come to it actually, but it does. You park it on a beach in Bangladesh and they take it apart, they make it land mourners, basically, and things like
And why
that.
don't you sell it to someone else? You can't get,
Well, at some point when it becomes 35, 40 years old,
I see, so there's a depreciation.
right, so the age. So what happens every period? You get some profit from basically transportation, offering trips to different exporters. And your profit is going to depend on basically your age, J, and the industry state, so how competitive is the market, how many young versus old ships. And then this variable D, which captures demand. So think of this as the macro condition. I'm going to say that there is an inverse demand curve, so think of this D, I mean, it's just in logs, but it's essentially this D that you care about is, in some sense, the intercept of the demand curve. It determines how much demand for transportation there is today. So with this demand curve and some nature of competition, I mean, I don't care, you can think about it as perfectly competitive, you're going to get some per period profits. Point is, I'm going to have a reduced form that tells me at a given age and market state how much my payoff is from operating. Okay, value functions. So the value function of a ship at age J at an aggregate age distribution, backlog, and demand is its payoff from operation plus the expectation for tomorrow, where if I exit, I'm going to get my scrap value, and if I stay, I'm going to get my continuation value. What's this continuation value VC? It's simply my expected value function tomorrow. Tomorrow I will be a period older. The state will evolve one period ahead, and that's that. And I'm taking expectations over number of entrants, number of exitors, and the demand. This is where the randomness comes into this model. What's the optimal exit policy? The incumbent will exit if the scrap value is larger than his continuation value. Right here, this is exactly what we saw yesterday. And so the probability, this amounts to the probability that your scrap value is larger than your continuation value, which depends on the distribution of the scrap values that we have. So essentially, the number of exitors is binomial because we each flip this, we each draw this scrap value that's IID every period, but since there is a lot of them, I'm going to say that exit is possible. Okay, entrance, it's going to be super simple. So here is the value of an entrant at a particular industry state. So an entrant decides to enter, but it's going to, there's time to build, so it's going to take cap T periods to enter this market. So if I'm an entrant, I need to take the T period ahead expectation of the value of a 0-year-old ship. So I need to predict what will happen to the age distribution, backlog, and demand in T periods from today. Okay? The time to build can change over time, so think of this as responding to market conditions, capturing the fact that there is queuing and when that people tend to invest at the same time when demand is high, for example. And I'm going to say that there is a free entry condition. So the value of entering is going to be equal to some entry cost. And going back to a question that arose yesterday, here the entry cost is reacting to market conditions. It's not going to be an IID shock. We're going to say that entrants will enter until this value of entry hits the cost of entering. Okay? And basically, you should expect this to depend on the number of entrants, right? It's like a standard free entry condition. If the more people I expect to enter, the less likely I am to enter. And it does through expectations. Because this value of entering has inside my expectations of how many people are actually going to enter the market. There is a Poisson entry rate, and this Poisson entry rate essentially solves the free entry condition, if that makes sense. Yes? They can perfectly predict the time to build that they're going to get. They know at what point they are going to enter the market. Okay? Okay. All right, so let me give you an... Yes. So the assumption is that each... it's too fast, I'm sorry. But basically, each potential... At the end of the day, it's very similar to the random entry cost. Essentially, every entrant is mixing. And the mixing probability is going to solve the free entry condition, is what happens. Okay, so let me give you an overview of the estimation, and then I might just take 5 minutes from my next lecture to close the results. So as I've been saying, the difficulty in estimating these dynamic games is precisely getting these value functions. Okay, so here, we're sort of going to do the opposite of what we've been looking at yesterday and today. So in all we've been looking at, we compute value functions, and from there we're getting entry cost, scrap values. Here we're basically going to use information on resale prices to argue that they're giving us value functions, and from there get per period payoffs, entry costs, and scrap values. So basically I'm going to estimate these value functions directly, and once I know value functions, getting all the other parameters is going to be basically an addition and a subtraction, and it's going to be extremely, extremely simple, and I think you're going to easily see why. So to estimate the value function, I'm going to use these second-hand prices, and basically I'm going to say that under these Stark assumptions, these resale prices are equal to the value functions, and there's only measurement error left. So ideally, I would want this regression to perform really, really well. Right? So there's nothing else that I'm losing inside this state that determines resale prices. But once I make this assumption, this essentially becomes a non-parametric regression. I'm going to take my resale prices and just regress them on ages and the ship age and the aggregate state of the ship. Now, you might worry about this both for sort of sample selection and adverse selection, and I'll show you. The good thing is that you have enough data to do some good external validation, and you'll see what I mean by that. And then there is some suggestive evidence that selection cannot be too severe. It's a very liquid market. You can explain, you'll see that the R-squares are in the order of 95 to 98%. These regressions, like age and aggregate stuff, perform really, really well in predicting these resale prices. And there seems to be, in terms of adverse selection, you hire divers that go underwater and examine the hull, and there seems to be sort of very clear information on the history of the ship and so on. So let me give you this, and then I will stop. The estimation will proceed in the following steps. I will basically first estimate some exogenous objects and some equilibrium objects, and then I will go to the primitives. Okay? So the exogenous objects are going to be the demand curve for shipping. This is going to give me as the state variable D, and I'm going to need a transition for D. And then this is a little tricky because I'm going to estimate a process that can generate a crisis. So it's going to be tricky to think about how to actually do this. The equilibrium objects are going to be value functions, and this again is just a non-parametric regressions because I'll assume that resale prices are giving us the value functions. And state transitions, and this is just BBL POB, it's just frequencies off of the data for how states transition. And then the interesting part is this. So model primitives, and now from here already you can see how this is going to go. So basically, I know the value function from here and the transition rule. I can immediately get scrap values because the density of a scrap value is simply the probability that a scrap value is smaller than my continuation value, and I know this. So that's very easy. Profits are very easy too because it's just going to be the value is profit plus expected value. I know value, I know expected value. I'm just going to subtract them and get profits. And then the entry condition is going to say the entry cost is the t period ahead expectation of the value function. So I know the value function, I know transitions. I immediately get the entry costs. Okay. So I will take maybe 5 minutes from the other lecture to just show you some graphs, and then we'll talk about another shipping application.